Today, I'll be reviewing basic aspects of meta-analysis, presentation prepared with my colleague and Michael Borenstein, and I hope you'll like to hear what I have to say. If I say something that you don't understand, please stop me whenever that happens. If it's a question to pursue some idea further, it's probably better to wait till close to the end of each segment. So I'm going to be talking about in 4 parts, but really I'm going to try to touch on 6 different areas. The first one is to distinguish primary studies, narrative reviews, and systematic reviews and meta-analyses. Then I want to talk about the basic components or parts of the meta-analysis. I want to talk a little bit about effect sizes, which are essentially the coin of the realm, or the basic building block of the meta-analysis, review the basic calculations, talk about heterogeneity or dispersion and why that's important and how we go about assessing it, and then to talk about the difference between the 2 major models in a standard meta-analysis, the fixed effect model and the random effects model. So first, I want to talk about primary studies, narrative reviews, systematic reviews, and meta-analysis, and what they have in common and how they differ. So, I suspect everybody in this room is familiar with the features of a primary study. You generate a hypothesis based on theory or observation and/or experience. You decide what population and in what setting you're going to use to test your hypothesis. You collect data from the subjects or participants or units. Say you're doing hospital-level studies, so you might compare hospitals rather than individual patients. You then do a statistical analysis, and you write it up in a report which you hope to get published somewhere and further your career. Okay? Systematic review is the same thing as a primary study. It's a form of research, and I'm going to suggest that the only difference between a traditional primary research study and a systematic review is that in a systematic review, the subjects are studies. Okay? That is really the only difference is who the subjects or participants or units of data are. Other than that, if you're going to be doing a rigorous up to 2014 standard systematic review, you're going to be generating a hypothesis based on theory and or observation and or your experience. You're going to decide what is the population of studies on which you can test your hypothesis. You're going to collect your data, which in the case of a systematic review consists of 2 components. First, retrieving the information, retrieving studies and reports, and then extracting the data from those studies that are relevant to your research questions. I always tell people, just think of it as that you're interviewing the studies and you're asking questions of the studies. And if they can answer, then you can include the data. Might not always be the answer you want, but they need to be able to answer the questions that you're posing. You then do the statistical analysis if it's appropriate. And if you know anything about systematic reviews and meta-analysis, you'll know that some disagreement occurs around the question of how heterogeneous your data can be before you decide it's too heterogeneous to combine and that you should not use meta-analysis. I tend to be fairly much of a lumper rather than a splitter, but even I have been known to say occasionally the data are too heterogeneous to meta-analyze. And one of the things I'll be talking about a little bit later is some possibilities for synthesizing your data that avoid some of the pitfalls of a narrative review if you're not going to do a meta-analysis. Because one of my pet peeves, and we discussed this in an article that I did with John Ioannidis a few years ago, is people who put in all the effort of doing a very rigorous systematic review in terms of the hypothesis, in terms of the retrieval, in terms of the collection of information. And then when they get to the data analysis part, if they don't do a meta-analysis, they kind of do some, what we call cognitive algebra, which is they use some unknown algorithm in their brain to combine the information, and then they tell you what the result is. So it seems to me that's a tremendous waste of information, because you're doing all of this scientific stuff till it comes to the let's put it together and see what the results are, and then people often fall back on a narrative review, or they think they're being more sophisticated and they use a vote count to tally up the significant studies. And I'll tell you in a little bit why I think that's bad practice. And then, of course, you write your report at the end, again, with the hope of getting it published, or in the cases of some of you, getting your doctorate. So, in short, a systematic review is best thought of as another type of research study, but in character, in purpose, in methodological rigor, it should really be held to the same standard. I've never figured out why people are so particular about how primary studies are done. It took so long for them to attend to the subjectivity and lack of rigor when reaching conclusions in a review of those studies. And so what systematic reviews and meta-analysis have been devised to combat is sort of sloppy combination of information when the stakes are important, like in patient care or in my field of origin, industrial psychology, who gets the job and who gets turned down for the job. Okay? Any questions about what I've said so far? Y'all with me? Good. Okay. So let's differentiate a meta-analysis from systematic review. Meta-analysis is just the quantitative data analysis. Not all systematic reviews include a meta-analysis. Unfortunately, at least in some fields, not all meta-analyses are preceded by a rigorous systematic review, which creates the opposite problem, which is that you don't exactly know where the data came from or whether they met scientifically rigorous criteria for inclusion in the study, but once they get there, you're very scientific about it. And so you have a very precise answer to a question that we're really unsure of. But in practice, if you talk to people who do meta-analyses, they are sloppy, which is probably unforgivable, but it does have historical precedent about using systematic review, meta-analysis, or research synthesis as if they were synonyms. And in particular, I think people in the social sciences, where the meta-analysis part was emphasized earlier than the rest of the review part, people are more prone to use the term meta-analysis to refer to the whole enterprise. Whereas in the health sciences, people will also often call something a systematic review without differentiating whether it had a meta-analytic component or not. So I try to use the term research synthesis because it's more neutral and it covers everything, but if I slip up and use the wrong term, forgive me, and if you're confused about what I'm actually referring to, please let me know. Okay. So a systematic review tries to conform to basic principles of what we would consider good science. So it tries to be explicit in terms of its statement of objectives, in terms of the materials that it uses, in terms of the methods that it employs. It tries to be systematic, for example, in the way literature is identified. So if you look at the section in a systematic review that discusses how the literature was identified, it's typically a lot longer than that similar description would have been in a traditional narrative review. Most important to me, I think, is transparency. Because it is possible, since this is a decision-heavy method, and I think a lot of scientific studies are more decision-heavy than they let on, because we like to pretend that human judgment doesn't really affect things, but it does. For me, transparency is important because people have to be upfront about the choice points, the decisions they made, and the rationale for those decisions. And I think that goes a long way towards resolving inconsistencies across reviews sometimes, but in the very least, you're not stuck with a cognitive algebra that is idiosyncratic in somebody's head and not articulated. Transparency should lead to reproducibility in terms of methodology and conclusions, and as you've probably been hearing for a very long time now, science needs to be public and reproducible. Okay, what goes on privately and what goes on that can't be replicated might contribute to some kind of knowledge, but it's not science. And to the degree possible, a systematic review aims to be unbiased. I'm not sure if anybody can ever really get all the bias out of any human activity, but at least systematic reviewers recognize the proclivity towards bias and attempt to minimize it when humanly possible. So by now, you're probably thinking about, well, why do people do traditional narrative reviews? And we can puzzle through that together because I don't quite get it. But in any case, the big problem with narrative reviews are that they're not scientifically rigorous. They use informal and subjective methods to collect information and to interpret information. A narrative review usually provides a narrative summary in words rather than any kind of numbers. And one of the big problems historically has been that different experts will do different reviews, ostensibly looking at the same research question and looking at the same literature and coming up with very, very different conclusions. Sometimes that actually can be pinned down to the fact that they looked at a different subset of studies, but sometimes even when they look at the same studies, they come up with different conclusions. And of course, another problem is that very often when reviewers agreed on a conclusion, it was that the research isn't conclusive, we need to do more research. Okay, now it's not so bad to say we need to do more research if your review shows that you've reached point A and now you want to go to point B. The problem in a lot of narrative reviews was that people kept trying to get to point A and kept saying we can't reach any conclusions. And after a while, funders are not so happy to hear that. And you end up undermining the credibility of the enterprise you're trying to develop by saying, well, we've done 20 studies now, but we still don't have the answer. Also, as research asks more complex questions, it's even more difficult for any human being to keep track of the amount of information that he or she needs to put together to reach a sensible conclusion. So in psychology, there's famous research from quite some time ago that led to someone formulating the principle of the magic number 7 plus or minus 2. And basically that says that people can probably keep about 7 pieces of information straight in their heads. They must have done it on college students because I don't think that I'm up to 7 anymore. I don't think it's going to get better. But so somewhere between 5 and 9 plus or minus 2. But a lot of reviews have a lot more information than that. And it becomes very complicated, both as the number of studies increase and as possible variations increase. And I'm left with the question, if we use statistics to combine information from patients in an individual study, right, why wouldn't we want to use statistics to combine information from studies? It just doesn't make sense. How would anybody accept it if you submitted an article to a journal that said something like, well, I looked at 50 patients' records, and based on my expertise and my deep understanding of the subject matter, here's the results in narrative form. Right? People would laugh at you. Okay, but people didn't laugh when you did the same thing looking across 50 studies. Just doesn't seem to make sense. Okay. And of course, when you want to investigate covariates or variables that moderate the relationship or the effect of a treatment, it becomes way more complex to keep the information straight in your head, and really based on good scientific evidence, it's just not possible for a human's cognitive capacities to keep this much information straight. We need some kind of decision aids. Okay. So let me give you some examples from some of the earlier meta-analyses or the earliest systematic reviews. People tend to think that systematic reviewing and meta-analyses were developed in the biomedical sciences, because certainly at this point in 2014, that's where the largest number of reviews have been done. But in fact, they were developed by social scientists pretty much simultaneously, working in 3 different fields. So in the area of social psychology, Bob Rosenthal and Don Rubin were looking at the effects of interpersonal expectations on behavior, what we now would call a self-fulfilling prophecy or a Pygmalion effect, where they were claiming that a researcher's expectations or a teacher's expectations, even when they try to mask them, gets communicated to the research subjects or the students in ways that actually affect their performance. Now we try to take that into account by things like, blinding when we're doing the study. Then also in the educational literature and in the psychotherapy literature, Jean Glass and Mary Louise Smith were interested in a couple of questions. And then in my own field of industrial organizational psychology, Jack Hunter and Frank Schmidt were interested in whether employment selection procedures developed in one organization were also valid if they were used in other organizations. By the time they came up with the idea of doing a research synthesis, there had been 345 studies looking at this interpersonal expectation behavior. There had been over 700 studies looking at the relationship between class size and achievement. There had been 833 studies looking at the effectiveness of psychotherapy. And there had been over 800 comparisons of whether the same tests were valid for black and white workers in the United States. Now, let me ask you, if you were a funding agency And someone had done 345 studies. And the narrative and a narrative review concluded, we don't really know yet. We need more research. The data are inconsistent. Would you fund the 346 study, or would you say there's something fundamentally wrong here? Okay. So one of the among many of the pushes towards research synthesis was people's concern that they would lose their credibility as a valid scientific enterprise by saying the results are inconsistent so much. And they felt that probably the results really weren't inconsistent, but we were just trying to get at them the wrong way. Okay? So let me just take one example, is class size related to student achievement. By 1978, around the year I was born, in other words, there were hundreds of studies on that topic. Okay, and a fellow named Thompson, an expert in the area of achievement, educational achievement, did a narrative review of the literature and said that the relationship involved too many complex issues to be reduced to a single testable hypothesis, and that research findings were necessarily inconclusive. So again, if things are necessarily inconclusive, what's the point of doing any research? We could go do something else like become professional football players. So Smith and Glass came along in the same year, 1978. They extracted 700 comparisons from 80 studies that met their criteria, and they were able to show clearly and statistically that smaller classes were better on three main criteria of interest: student achievement, classroom processes, and both teacher attitudes and student attitudes. Now, this research has been refined. It's not necessarily a completely linear relationship. Nevertheless, they were able to actually show solid findings. Yes, class size matters. Okay? And it should not have taken so many studies to be able to do that, but nobody really combined the information meta-analytically before. Okay. So, just in case anybody asks you, what are the differences between narrative reviews and systematic reviews? In the systematic review, criteria for inclusion are determined ahead of time. As a matter of fact, those of you doing systematic reviews will know now that you need to write a protocol first, the same way you would do any other kind of research. You can't just make it up as you go along. And if you want to do a review for the Cochrane collaboration or for the Campbell collaboration, you need to get your protocol approved before you can start doing the review. And protocol review or protocol development, first of all, it's resource efficient, but more importantly, it enables us to keep track of biases, because you can't change your mind as you go along depending on what the research looks like. So your criteria for inclusion of a study is determined ahead of time. Your hypotheses are determined ahead of time. You have to outline the methods you're going to use to collect your information. You're going to have to describe to somebody else how you're going about pulling the relevant data out of the studies that you include, how you're going to code different features of the studies and what features you're going to code. So that all has to you have to put your money down on the table before you spin the wheel. Okay? And meta-analysis or some other objective means of combining the data is usually possible, and it should be replicable, although journal reporting practices and page limitations being what they are, you are often not able to report everything that you would want to report to make the analysis replicable. I always tell my students, A, they should keep a log the same way you would keep a bench log in the lab of everything going on, and B, that you should have a drafted report with everything in it, so that when you have to trim it down for publication, you still can say the other information is available from the author, or you can, in some of the new electronic journals, or you can actually have hyperlinked data for people who want to drill down further on particular issues. I'm particularly keen on having people keep the logs, though, because you'll find that the things that you think you're going to remember, you don't. And if you don't write them down, when you do them, some of them are going to be gone forever in space. And it's just like, I still can't believe that I didn't write down when my children started walking, because I'm sure it would be engraved in my brain forever. And when they ask me now, I have to make stuff up. I don't mind doing that to tell my kids, but I really don't want to do that when I'm trying to publish a paper. It's really not ethical. So, so write stuff down. Write down even what you're sure you're going to remember. Okay? And probably write it down in consultation with one of your colleagues on your research team. Okay, so just again to contrast the narrative reviews, people don't have to put their money down where their mouth's going to be at all, right? No one has to see a protocol of the narrative review. And even if you're trying your absolute best to be honest and objective, if you've looked at any of the literature on human judgment and human decision making, we are filled with biases. Danny Kahneman won a Nobel Prize for pointing out some of those biases. And something like a protocol and all of this objective description does a lot to keep us more honest, even just to ourselves, beyond talking about dealing with the scientific community. Okay. Any questions up until here? Have I all convinced you should not believe narrative reviews? And you should probably be a little skeptical about systematic reviews? Okay. I want to talk about vote counting because even in 2014, I see people use vote counting a lot when they can't actually or they won't meta-analyze their data. And so I want to run through vote counting to make sure that none of you do it. And I do promise that if you're tempted, I have 2 better ways of doing things that are not state-of-the-art meta-analyses, but avoid at least some of the pitfalls of vote count. Okay, does everybody know what a vote count is? Yes? Now raise your hand if you know what a vote count is. Okay, no, but, okay. Lara? Okay. You know. You've seen them.
Yes.
Yes.
But it's basically when if you have a set of studies, including studies that the authors don't feel that they can meta-analyze, they say, well, this one showed a statistically significant result, so yes, this one showed it.
Right.
Not statistically, so no. And then they just say the number of studies showing yes.
Okay. And should I ask you why that's bad, or should I tell people?
You can.
I can tell you. You sure? But okay. So in vote counting, you collect a set of studies, right? And you can even use the systematic review, rigorous, objective ways of collecting data, apply your inclusion criteria, and then say, I can't meta-analyze these. Either they're too heterogeneous, the effect sizes aren't extractable, and therefore I can't combine them because there's no statistical way of doing it. So that what they end up doing is looking at the test of statistical significance. Draw a line down the paper, you have 2 columns, study 1, to find significant results, yes or no. Study 2, 3, down to N, yes or no. So significant is a yes vote, non-significant is a no vote. Sometimes there is a variation where you'll have statistically significant positive, statistically significant negative, because sometimes reversals do occur, and non-significant. And then, because democracy rules, the majority wins. Okay. So, what's wrong with that? Okay, here's a look. This is from 1982, so this is a bit old. It's from Psychological Bulletin. but it provided a good example. You can see they have a plus and an NS, and then they tally them up. And then, okay, so note on the bottom, plus equals positive, NS equal non-significant, and they explain that correlations identified as positive are those in which employed women have significantly higher psychological well-being than those who are unemployed. No cases of a negative association between employment status and psychological well-being were located. So if you're a working woman, you have higher well-being, and you should relax when people tell you that. It's not good for your kids. Okay, so what's the problem with statistical significance testing? Okay, now, the problem with vote counting here is that it treats any non-significant probability value as if the effect were absent. And as your statistics teachers probably have tried to drill into your heads, absence of evidence is not the same as evidence of absence. So what you should be concluding when you have a non-significant p-value is that the evidence is inconclusive, or that we don't have enough evidence to say whether the effect was due to chance or whether it is a real effect. That is all you can say. It doesn't mean that the effect wasn't there. It just meant that you couldn't nail it. Okay. And we know that we can get certainly small or moderate effects, non-significant, just because we ran our study on too few subjects and we didn't have sufficient statistical power to reach significance. So the bottom line is that vote counts, for one thing, often are wrong because the primary studies had low statistical power. And certainly when you're running studies with 9 people in each group or 25 people in each group, you can have quite a large effect without being able to find it being statistically significant. Something that would be a clinically important effect can still be statistically non-significant. Okay? Hedges and Olkin, and Larry Hedges is like the father, and Olkin is the grandfather of meta-analysis, actually had a paper as early as 1980 showing that often the power of a vote count to reach the right conclusion was lower than the primary studies that were included in the vote count. And that actually, this is a very bad thing statistically, that power could actually go down, power to reach the correct conclusion would actually go down the more studies you had in an analysis. So in other words, if you had enough studies done with sufficiently low power, you could be absolutely confident and wrong at the same time. Okay? So if you had 20 studies, each having 30 subjects, and an effect size of 0.5, I don't know if you're familiar with standardized mean differences, but essentially what a standardized mean difference of 0.5 would mean that the average person in the treated group would be half a standard deviation better than the average person, the person at the mean of the control group. So that's a really substantial difference, okay? So that will fail to, a vote count will fail to declare significance, the winner, 75% of the time. Okay, and we clearly don't want to mess with any technique that becomes more misleading as the evidence increases. It's just science, it's not supposed to work that way. Okay, so you get a bunch of studies with relatively small samples, which lead to low power to detect the effect, and the more of them there are, the more likely your vote count is going to reach the wrong conclusion. Even when vote count, yes ma'am?
I'm sorry, I want to ask you something about sample. It's a because I'm a psychiatrist and I did a lot of research about psychotherapeutical treatment effects. And we have really problems with how to create samples because we have inclusion and exclusion criteria.
Yeah.
And that's not a real picture of the state of art, you know. That's a really problem. I think that maybe also give a part in this why is this situation with these meta studies? Because we have a quite different sampling between different studies.
Between the research studies and the people you see in your ordinary practice, or between different research studies?
Between different research studies.
Okay. Well, when we talk about heterogeneity, we're going to talk about being able to figure out what role having different patients or populations might play in a meta-analysis. Okay. I thought you were going to say because you're a psychiatrist, you sometimes have to deal with very small samples, which relates to the thing of vote counting. I know that's often a problem. So one of my sons is a psychiatry resident, and when he was doing research, one of his jobs was collecting informed consent from people. And I know how hard it is to get people to sign up. So we will talk about trying to put together a picture from samples that are different from each other, and we'll also try to talk about the fact that sometimes research samples don't really mirror the clinical population that you're dealing with on an everyday basis. So thanks for asking that. Okay, so just to conclude about vote counting, so even when vote counting actually reaches the overall correct conclusion, so the treatment worked or the treatment didn't work, it still falls short in a couple of important ways. It doesn't tell you how strong the effect is. So saying that something was significant could mean that you had really big samples, and therefore you were able to declare as non-chance a treatment effectiveness that really is very minor. Or it could mean that you had really strong effects, but you couldn't tell the difference just by looking at significance level. And also, the other problem with vote counting is that it uses unit weights. It treats a study of 20 people and a study of 500 people as if they had the same information value. And one of the things that I'll be talking about when we switch to actually looking at the basic components of meta-analysis is that in meta-analysis we want to give more weight to studies that are more precise because we believe that they have more information value. Other questions?
What is the alternative to vote counting?
Okay. You anticipated my next section. So I'm going to propose two methods to combining the data when, for whatever reason, you're not comfortable doing a formal meta-analysis. One is an old, and they're both really old methods. One was developed particularly for synthesis purposes, and the other one is just an adaptation of a test that was developed to look at primary studies. Okay. So the first thing that I want to talk about is doing a combined significance test meta-analysis. Okay? And this was actually based on Bob Rosenthal's first go at meta-analysis, where he basically wanted to look at a bunch of inconclusive primary studies and say whether overall the effect was significant or overall it wasn't. Okay? So across the body of studies, did the effect appear to be significant or not? And the advantage to this type of meta-analysis is essentially it just increases the power of the the overall comparison compared with the power you would have in any of the component studies. So the logic here is that, let's say you have several tests that are consistently in the right direction. Okay, so they all look as if the treatment is working, but none of them reach conventional levels of statistical significance. You can hypothesize that the reason that they are not statistically significant is in fact due to the low power of the studies. And you can pool the information and conduct a significance test of the all of the studies put together. And because once you pool, and you're not pooling the individual data points, you can't do that because the studies are too different. But if you actually pool the information from the summary significance levels of each study, you, in effect, create a more powerful and larger base. Essentially, but what's really important to realize is the hypothesis you're testing. Okay, the null hypothesis, your null hypothesis is that the null hypothesis is true in all of the studies. So if that hypothesis is rejected, all you can really say is that there's at least one study in this file that has a real effect. You can't conclude that they all reached real effects, okay? And again, it tells you nothing about the magnitude of the effects at all, okay? And here's an example. This is from the Journal of Clinical and Consulting Psychology. It's also quite old because it was sort of the only meta-analytic game in town when this was developed. And essentially, what you do is, this was based on correlational data, but the correlational data are converted to z-scores. You then, this is the z-scores, but let's assume that those were actually probability values, and it'll be easier to explain. You basically collect all of the p-values. They're numerical values, not significant, so like 0.07, 0.01, 0.23, whatever. Then you compute an overall p-value. I'm not going to get into the technical parts of it, but I can recommend Betsy Becker's chapter in the Handbook of Research Synthesis, where she talks about several methods. The one that was used in this study was the Stoker's method of combining Z's, so that essentially you back compute the Z's from the P's, you sum the Z's, and then you compute the overall p-value. But you're not going to remember that. And then once you compute the overall p-value, you can basically say that there is an effect or there's not an effect. And we have better methods now, but sometimes, for example, when you have a lot of studies that only report a p-value, they don't report any effect sizes, and otherwise you would have to just ignore them. You can at least do this. Or if you have studies that are done on very different metrics, so that you really, they have a lot of different effect sizes. Some are based on correlation, some are based on standardized mean differences, some are based on binary data, and you're not comfortable combining all that information, but you are comfortable saying, I think the general question they're asking is similar enough to kind of be able to give an overall sense of does it work or does it not work? Again, this would be a reasonable way to proceed. And again, if anybody wants directions towards where the technical parts of these analyses are discussed, or there's probably some software around still that does this too. Okay, so as I said, an advantage to this is if all you have is the results of significance tests, and certainly in at least you found this. So Okay? If you only have the results of significance tests, some journals, and particularly older journals, sometimes let articles only report significance tests. You can find different test statistics, as I mentioned, and everybody thinks they understand p-values, even when the notion of effect size scares them. So sometimes if you're trying to get the basic point across to a general audience, that is a good thing to do too. Disadvantage. The same issues that I mentioned before with primary studies and vote counting. A p-value is a p-value is a p-value. It doesn't tell you anything about the size of the effect. So you can have a large effect that is not significant, or you can have a trivially small effect that is significant, again, based on your sample size. And if you're going to be doing an overall p-value meta-analysis, the biggest concern would be that, yes, it is statistically significant because you've combined so much information, but in terms of clinical or practical value, it's really a tiny effect and nobody would care. So you have to watch out for that. But if you don't have the information to do anything more, it is better than a narrative review or a traditional vote count. Okay. Another possibility is the sign test. Does anybody remember the sign test from basic statistics? No? Okay. So basically, a sign test is a non-parametric test, okay, and it's kind of similar. Think about the vote count. And I said you draw a line down your paper and you vote yes if it was significant and no if it was non-significant. You do the same thing here, except, and this is a key difference, you vote yes if the direction is the right direction, and you vote no if the direction is the wrong direction. Okay? And if something has, you really never get 0 if you go out in decimal places, so I'm not even going to make a comment about that. So in other words, you ignore statistical significance, you just look at the direction of the effect. Okay? Now, if the treatment is completely ineffective, what would you expect to look at once you went down the line and summed the two columns? Anyone? If there's no treatment at all, what's going to happen by chance? Right? 50-50. Half the time it's going to be positive and half the time it's going to be negative. Okay? So what you test with this is whether the departure from 50-50 is significant. Simple idea. So if a treatment is completely ineffective, in other words, chance is the only thing that's going to be operating, you should have half the study showing positive results and half the study showing negative results. So what you want to do is you want to test the departure from the proportion of positive and negative you would expect if there was no real effect. Okay? So your hypothesis that you're testing here, your null hypothesis, is that the effect sizes from this collection of studies are all really 0. Okay? And then you go, and the test you actually do is to see whether the proportion of positive results in the direction you hypothesize, is statistically departing from 50%. Okay? If the treatment has an effect, the probability of getting a significant, probability of getting any positive result is going to be larger than 0.5. If it has no effect, the probability is going to get 0.5. If in fact it's killing your patients, you should have more on the negative side, or if you're looking for any kind of adverse effect. Okay? Sign test is useful when you don't have any numeric data from the studies at all, but the author said something like the effect was in the expected direction, or not. Okay? Or when the data the underlying data are so different, you don't want to say that they're really the same population, but again, whether it would be useful to know whether the effect was in the right direction or not. Or the studies are really very diverse, or whatever. So when all else fails, you can use the sign test. It probably requires even less information than the combined p-value test, because sometimes people don't even report p-values. They just report expected direction, not expected direction. And for those of you who like statistical significance testing, I have to say I'm not a big fan. You can test your results for statistical significance using the standard binomial test, the equation for which is really pretty easy. The disadvantages, again, are the traditional disadvantages of any sort of not quite meta-analytic technique, that you don't get an estimate of the actual strength of the effect or strength of the relationship, and you're basically giving equal voice or equal weight to all of the component studies, whether they were based on 10 people or 10,000 people. And as I mentioned, we think that weighting by the information value in a study is probably really important in most cases. Okay, so does that answer your question? Okay, good. Okay. Any other questions about this? Okay. You want to look at an example of the sign test? Okay, I looked it up just for you, so I hope you'll say yes. Okay, so this is from Bravada et al., 1999, where they were looking at the effect on quality of life of patients post-liver transplant. Okay, and I guess liver transplants are expensive things, and they come with side effects, and so they wanted to see in some way whether it was worth it. And so what they did was they just looked to see whether people indicated that their quality of life had gotten better or worse after the liver transplant. They looked at 49 studies using the sign test, and they showed that they had significant improvement on five criteria, but on the sixth criteria, they did not find a statistically significant difference, which does not mean that there was no difference, but that they couldn't rule out chance in that particular case. Since they did the test on the same 49 studies for all of the outcomes, this is one case where you probably could conclude that the p-value was a good stand-in for the size of the effect, because it was all based on the same information. So the only thing that would really be different would be the effect size. But they were able to say that, yes, the transplantation improved people's quality of life on 5 out of 6 criteria. But we can't really say by how much based on the tests they were talking about, and we can't really say whether all the studies showed the same amount of benefit, or whether there was something about the different studies that led to different amounts of quality of life improvement. And since those are things that we usually want to know about, when possible, we want to use traditional meta-analytic techniques, because they can both provide how strong the effect was, and they could tell us something about whether the effect is similar across situations, or whether there are particular features of patients, settings, dosages, or whatever that influence